Over here, I've modeled a sort of situation. There is a stone which falls off from height h, which is a cliff of height h. No external forces are acting on it when it's thrown. And it hits a rocket which is launched from the bottom, so over here. And it flies up and it hits it when the rocket is at its maximum height. The acceleration of the rocket can be modeled as a minus bt, where a and b are both positive constants. This question is taken from the MIT Open courseware on their Kinematics and Dynamics course. All right, so if you think you can solve it, go ahead and try it. But if you want to find out the answer, stick around here and I'll walk you through it. All right, so first of all, let us figure out what we're going to do to solve this problem. Why don't we first make an equation for the position of the rocket, make an equation for the position of the stone, and set them both equal to each other. Why is this? Well, we know that the stone and the rocket both hit when the rocket's at its maximum height. So if we find an equation for the stone's position as a function of time, at the rocket's position as a function of time, set them equal to each other, we can find out the time where they both hit, and we'll also get an implicit formula for h. So all we have to do is just rearrange and we get the height. So let's start off. Why don't we first find out what the position of the rocket is? Well, let's make a note to ourselves. So note on how to find out position. Well, we know acceleration. So how can we get acceleration from position? Well, we know if we take the area under an acceleration time graph with respect to time, we're going to get velocity as a function of time. And if we furthermore, if we get the velocity as a function of time and we take the area under that graph, so the integral of velocity as a function of time, dt, we'll get our position as a function of time. And that's what we want. Lucky for us, we actually have already acceleration as a function of time. It's right here, a minus bt. So why don't we integrate that twice, knowing our upper bound and lower bound, and we get some position as a function of time for the rocket. Okay, so if we take the integral of a minus bt dt, that will give us the velocity of the rocket. But what are our bounds? Well, first of all, since this is a snapshot at time t is equal to 0, we can set our lower bound straight away as t is equal to 0. Okay, but what's our upper bound? If we're trying to find out velocity as a function of time, we should just say that the time here is going to some arbitrary point in time, t. Now, this would be fine. However, it draws a little bit of confusion when we say t is equal to t. So what I can do is dt is a dummy variable. I could just put a little dash on all the t's I see, just to clear up the confusion that this t and this t are not the same t's. Okay, so from basic calculus, you should be able to see that a is basically a times t to the power of 0. So that'll give us a t when we take the integral of that, because as the power rule suggests for integration, x power of n, if you're taking the integral of that, we'll get x power of n plus 1 over n plus 1. So 0 plus 1 over 0 plus 1 gives us just x power of 1 over 1. So at, and over here, using the same logic, power rule, we'll get bt squared over 2. And that right there is our velocity as a function of time. Okay, let's integrate the velocity as a function of time to get our position as a function of time for the rocket. Let's take the integral from the same limits, t is equal to 0 to t is equal to t. Again, let's put a little dash on all the t's so we specify that t dash is not the same as t of at dash minus bt dash squared over 2 dt dash. That will be our position of the rocket as a function of time. Again, this is a bit more complex than the first example, but not too complex. We'll get that it's at squared over 2 minus bt cubed over 3 times 2, which just makes 6. So I can say that the position for the rocket, which I'll call r sub capital R, as a function of time, will give us at squared over 2 minus bt cubed over 6. I'm just going to box dot off in pink. Okay, we're going to come to that later. Let's first find an expression for the stone's position as a function of time. Well, since the stone is falling from a height h, let us use the kinematics formula to sort of derive some sort of equation for the stone. Okay, so let's say for the stone. Well, let's remind ourselves of the kinematics formula. So note, our height or our displacement is a function of time, which we'll call y of t since it's acting in the y-axis, is going to be our initial y height or initial y value, plus the velocity, the initial velocity in the y direction, so v naught y times t, plus half times the acceleration in the y direction, a sub y, times t squared. That is kinematics formula. So let's plug in what we know into this formula to get some sort of equation for the stone. So let me say r sub s, so the position of the stone as a function of time, will equal to our initial y height. What's that? Well, the stone falls from the cliff, and the cliff has a height of h, as you see here. So we can say h is our initial y height, or y sub 0. So r sub s of t is going to equal to h. Well, since there are no external forces when the stone is falling down, it's not going to have any initial velocity, or its initial velocity is going to be 0. So we can just cut off that term completely, essentially. Okay, what about the acceleration of the y direction? Well, acceleration will be g. However, we've chosen our positive j hat direction as upwards. And as we can see here, g acts downwards. So to clear that up, we're going to have to call that negative g as it acts in the opposite j hat direction. So we're going to say that this is equal to negative 1/2 g times t squared. And that right there is our position for the stone. Okay, the question also says that they both meet when the rocket is at its maximum height. So let's say for the collision, the position of the stone is going to equal to the position of the rocket, and the rocket is going to be at its maximum height. So for the collision, h minus 1/2 gt squared, r sub s of t, is going to have to equal r sub capital R of t, which we found out was at squared over 2 minus bt cubed over 6. So this is going to equal to, just rub this out, at squared over 2 minus bt cubed over 6. Now this is great. All we have to do is just rearrange this term over here to the other side, and then we get an expression or an equation for the height. So h is going to equal to at squared over 2 plus 1/2 gt squared minus bt cubed over 6. I can clump the t squared over 2 term here. T squared over 2, a plus g minus bt cubed over 6. But wait, we're not done. See, the height of the cliff, it's going to be constant, well, in this short space of time, assuming that, there's not much factors affecting it. The height of the cliff is going to stay constant throughout this whole collision. So we do not want it to vary as a function of time. I don't think cliffs vary that much as a function of time in a very short space of time. But how do we find out the time t? Well, we know at time t, where they both collide, the rocket's at its maximum height, aka the velocity of the rocket is going to be 0, where the change in position is going to be 0. So what is our change in position? Well, that's going to be velocity, which we found was at minus bt squared over 2. And that's going to be equal to 0. That's the velocity of the rocket. It's a function of time. So rearranging this, we can get t. We can get a sort of an equation for t, and then plug that in back to back to this equation for height in the t squared and t cubed terms. So let's rearrange this a bit. We get at is equal to bt squared over 2. Now, we can cut out a t actually, because we obviously know t is not going to be 0, because as we see here, this is time t is equal to 0. And the rocket and stone obviously haven't collided that. So we can just cut out a t. So then rearranging this, we can times 2 on both sides. And we can divide by b on both sides. We get that t is equal to 2a over b. Now let's plug this value back into here. We should get that h will equal to, so element of truth, t squared, which was 2a over b whole squared, divided by 2 times a plus g. Yep, minus bt cubed, so minus b times 2a over b cubed all over 6. Now that right there is our final answer for the height of the cliff. I'll just highlight that so it makes it obvious.